So hello everyone, my name is Vikas Kumar Singh and today we are going to solve assignment number 5 of the course Mechanics of Sheet Metal Forming. It's online course, a theoretical course is going on. So I hope you people are attending the course. So you might have come across this assignment and mm, chapter number that textbook is also shared with you. So if you are following that textbook, you might have seen so many problems, assignment problems are directly from that book, solved example or exercise, and all the concepts are coming from that book only. So it is easy for you guys to learn if you are following that book, textbook, and textbook is uploaded on the website and it is also there on the in the Google Drive. You can check it out. The link is shared already. So we are going to solve assignment number 5 today. And the first question is, what is the uniform strain of a sheet material having imperfection ratio 0.005 following sigma equal to 200 into epsilon to the power 0.25 during the hardening? Okay. So in the lecture class, if you have attended, you will be knowing what is the imperfection ratio. Okay, so imperfection ratio is giving the it's just represent the localized weakness in a material. Localized weakness, you can say it's a like a ratio of major principal stresses in a uniform region. And the major uniform stresses in a perturbed region, or suppose some groove is there and all. So suppose like this kind of things are there. This kind of things are there. So stresses, if you are or some holes are there. So what will happen here? The material, the stress will be not homogeneous. Like this material is not there in the material. So at this cross section stress will be different. At this cross section stress will be different. So how to represent this imperfection ratio? So it is just defined imperfection ratio. F is defined by sigma 1 divided by sigma 2. And this is in one direction, homogeneous, and this is in a perturbed direction. Okay. So this value is given here 0.005. Now, coming to the solution. And generally, this value is less than equal to 1 in the practical cases. And this value is generally it is close to 0, like it may be 0. Sorry, this value is less than equal to 1. And what is happening here, if generally people will give in the question, means question whatever it is coming, so many assumptions are there, but in a practical ratio this is varying from varying this value, and coming always it is remaining less than 0, less than equal to 1. Okay, so coming to the solution, so this formula, like if you are knowing n is nothing but your strain hardening exponent, n minus eu, and the EU is the strain equivalent, uniform strain or equivalent, you can say. So this is nothing but root under minus of strain hardening exponent into minus of imperfection ratio. So this formula we are going to use here, and this value is nothing but it is given 0.005. Okay, 0.005. So this minus sign is already here. So this minus sign is considered here already. So if we are not considering, this will be 0.005. So we are not going to put it again here. So this, you can say this is a small error, or you can omit this. So minus sign is already taken care. So this formula can be written like this. And now if you are putting n value is 0.025, this value is coming from here. And imperfection ratio is coming from here. So I'm just taking the magnitude in the original formula. So if you will substitute, you will get the equation for epsilon u. And what is here? It is asked uniform strain. So EU is nothing but uniform strain, uniform strain. Okay. So this is asked. So this equation, this formula, this will come from directly from here. If we will put all this value and if you will take this 0.025 in this direction, so this you will get easily 0.021. So this is a very simple question. So it's nothing big in this one. So moving towards the next question. So we have next question. here select the correct limit strain value. This is one of the major strain and this is another major strain in a plane strain. So obviously in a plane strain, only two will be strain from the choice when a tensile fails as per the maximum tensile line epsilon 1 plus epsilon 2 means this is the formula what that material is following. The sum of these two strain will be 0.025, sorry. Now see these are the options. So if you will sum it up, this plus this will also be applicable. This will also be applicable. This will also be applicable. This will not be applicable. But we have to choose only one out of these two, out of these three. So for this, one clue is given here is a plane strain. So if we are talking about a plane strain and sigma 1, sigma 2, sigma 3 are there. So generally in the case of plane strain, this value is 0. Okay, so you can see this is also valid, this is also valid, this is also valid, but this is not valid. But we have to choose only one, and for that, just we have to check in which case this one is 0. So this one is 0 in this case here. So this will be the only option. However, the question specifically say in plane strain. In plane strain, one of the principal strains, typically epsilon 2, is 0. Okay, so this is the condition. If you will put this, so this option will be correct. So we have the correct option. Okay. So yeah, this was also a simple question. So now we are moving towards the next question, and question number 3. In the question number 3, it is given what is the strain at maximum load during tensile test of the gauge region of a steel strip that follows hardening laws of this. Sigma equal to K into epsilon naught plus epsilon. So in the previous assignment also I discussed this formula. Here epsilon naught is pre-strain in the material, pre-strain, and some value is there. So this is one of the modification in the power law. Like sometimes people are adding pre-strain, sometimes people are not adding. So when they are not adding, it is assumed that the material is directly coming from the cast process, or there is no forming. Basically, there is no forming on that pre-forming of that material. So pre-strain is 0 in that material. But if people are adding this, it means before going to further forming process, already material has gone through some forming process and some strain is there in the material. So this is the meaning of this. Now, in the question that follow, what is the strain at maximum loading? So one concept here again, we have maximum loading is the peak point of the stress strain curve. Like if you will see engineering stress and strain curve here, so this is sigma and this is epsilon. Okay, so this is following something like this, suppose. So at the peak point here, at the peak point, what will happen? Peak point maximum value. So suppose we have epsilon equal to K into epsilon to the power n. So at the what will be the slope at the peak point? We have to just find out what will be the slope at the peak point. So according to this question, we have to find out what is the strain out of this four. What is the strain? So you can see here at the maximum load, peak of the engineering stress strain curve, necking begins, and the condition for necking is this. Condition for necking is this. So how this is coming? One of the question, how this is coming. So I will show you. So see, suppose we have this formula. And okay, and you can just take d sigma by d epsilon, So what will come? This will come a into n into epsilon naught plus epsilon to the power n minus 1. So n minus 1, I am just writing epsilon naught plus epsilon here. So here n and this denominator, this will be the term. So if this is going up, this will be minus 1. So this will be the differentiation. Now, what is happening here? If you will take this n by epsilon epsilon naught plus epsilon, n by epsilon naught plus epsilon, this term outside, and k into same thing epsilon naught plus epsilon here to the power n. So this is nothing but, again, we have this term is nothing but your sigma only. So we can write it, this one, sigma into this term, sigma into this term, this value. And at the necking, when necking begins, that the maximum strain condition, at that case, this term is equal to this term. So this will be 1. So this will be 1. So that's why here it is directly written sigma, d of sigma by d epsilon is nothing but sigma. So this formula is coming from there. Okay. So now, if power law using this, we are using this is already given. So the strain at the maximum load, also called the uniform strain, is given by this formula you are knowing. Now, n is given 0.22. So sigma u equal to 0.22 minus sigma naught. So this is nothing in this question, just we have to use this formula. This is an extra term what it is used here, but it's okay. It's better to understand what is happening, the mechanism. Okay. Now, so which one will be the correct option? So this one will be the correct answer for this. Now moving towards the next question, and next question we'll see. So here in the next question, it is given that a steel sheet with inhomogeneity factor of, again, here concept of inhomogeneity is coming. So already we have discussed what is inhomogeneity. So we will use that concept directly. F equal to 0.009. Okay. 0.995 is deforming in a balanced biaxial tension. Here one concept is there, balanced biaxial tension. We need to understand this. What is this balanced biaxial tension? With sigma 1a, sigma 2a as a principal stresses in the uniform region A. What is the major principal stresses? Sigma 1b in the groove B at a small effective plastic strain of 0.05 if the material follows this rule. Okay, hardening model, find the value in MPa. So we have to find out the sigma 1b. This value we have to find. And uniform balanced biaxial tension means it's nothing but when we are biaxial means in two directions we are applying the stress. So material is deforming in two direction, not unidirectional. So what is happening here? Balanced means this 1 and 2 will be equal. Both the stresses, what is coming, will be equal, balanced. Okay. And this is the biaxial. And when we are talking about the balanced one, balanced means these two are equal, and alpha value will be what? Sigma 2 by sigma 1, sigma 2 by sigma 1, and this will be 1. Okay. So this is the state of stress in the case of biaxial balanced biaxial tension. And what about the strain? Strain we don't know. Means strain, you know this epsilon 1 plus epsilon 2 plus epsilon 3 equal to 0. So state of strain will be epsilon 3 equal to minus of epsilon 1 plus epsilon 2. This will be the state of strain. Okay. So what next? So inhomogeneity factor is given here. Okay. Effective strain is also given. Hardening law is also given here. So for biaxial tension, this one already I discussed here. This is the thing. So alpha will be 1. Now, just putting all this value, so we can find out what is the hardening according to the hardening law. What is the average strain average strain, and all values are given. Only we have to put the average stress or equivalent effective strain. Effective strain you can put, then we will get the effective strain. Sorry, stress. So after putting this value, it is given. So we will get this value 334.68 megapascal. Now we know the biaxial balanced biaxial. It means sigma 1 equal to sigma 2. So directly we can say sigma 1 will be equal to this formula, sigma 1 A equal to sigma 2A. This is equal, and this is equal to nothing but this value. So this is going to be sigma 1 A. Whatever value is coming will be equal to sigma 1 B, sigma effective, and this is equal to nothing but our sigma 1 B. So this again inhomogeneity factor, considering the inhomogeneity factor. Yeah. So this one value we will get. So if inhomogeneity factor is 1, so this will be equal to this. This will be equal to this. Why? Because in the previous section, what we discussed, inhomogeneity factor is coming from sigma 1A divided by sigma 1B. So in ratio of principal stresses in two major direction. So in one direction we got, and this ratio is given. This ratio is given this. So in another major direction, just we have to manipulate this equation. Just we have to calculate this equation. Sorry. Then we will get the sigma 1B directly. So this is our required answer. I hope this is clear. So in this question, the concept was what is the inhomogeneity factor, and then what is meaning of balanced biaxial tensor. Then we discussed the balanced biaxial tensor and inhomogeneity factor. Now moving towards the next question. So next question is similar to the previous question. Only thing here, alpha is given. Alpha is given means what? Alpha in the previous question we discussed sigma 2 by sigma 1. This is given. This value is 0.98. In the previous question it was 1. So what in the previous question we did, here we took 1. We have to now consider 0.98, nothing else. Okay. So same question. What would be the minor principal stresses sigma 2B in the groove region? Now this time it is asking when sigma 1B is reached, sigma 1B is reached to a value found out in the previous question. Okay, this one value what we got in the previous is given now. So what is the sigma 2B now? So alpha is given here. Alpha is given. And from the previous question, we have sigma 1B in this direction. Just use alpha, and sigma 2B as alpha is nothing but the ratio of these two stresses. So a sigma 2B easily we can calculate just by putting this value. So it's a very simple question. So we solve this. I hope this is clear, and our final answer will be this one. So now in this assignment, what we learned is one of the thing was inhomogeneity factor, imperfection. First was the imperfection ratio. Imperfection ratio. And sometimes people are calling this inhomogeneity factor also. We can say F. And then this was nothing but the ratio of stresses, major stresses in two directions, sigma 1A, sigma 1B. Now we learned this value is always less than equal to 1. And this is representing nothing but the localized weakness in the material, in the sheet during the forming process. The next what we learned is power law was A equal to epsilon to the power n. And sometimes people are adding pre-strain in the material, and this equation is modified like epsilon naught plus epsilon to the power n. And this epsilon naught is the pre-strain, and this is nothing but when suppose you are going to do some forming process. So maybe material is already formed in some other process, and that there is already induction of strain. So that induced strain beforehand is nothing but epsilon naught here. And the third thing what we learned, that at the necking point, like d of sigma by d of epsilon equal to sigma. In this case, our this value was equal to n. So if free strain is there, then this will be, or if it is not there, then epsilon equal to n. And the next part what we learned is what biaxial, balanced biaxial, balanced biaxial. So balanced biaxial is nothing but your stress in the two direction will be equal, and if alpha is 1, it means this is equal, means alpha is equal to 1. If they are not equal, so alpha will be the ratio of these two. So alpha will be the ratio of the stress. And similarly, in the previous assignment also we have learned like beta was the ratio of strain epsilon, epsilon 2 by epsilon 1. So in the case of balanced biaxial tension, it means a state of stress was sigma 1 equal to sigma 2 and alpha equal to 1, and a state of strain was epsilon 1 plus epsilon 2 plus epsilon 3 equal to 0. Then epsilon 3 will be minus of epsilon 1 plus epsilon 2. So all this concept I hope is clear. So we'll stop it here. So next, I guess next assignment will solve very soon after this. So this video will be uploaded on the website, so you people can directly access it. So thank you. Thank you all.